Hi everyone, my name is Hongsh. I'm very glad to have this opportunity to share our latest work in IEEE S&P conference. The paper is Learn What You Want to Unlearn, Unlearning Inversion Attacks Against Machine Unlearning. The authors are Hongsh from CSIO, Shuo Wang from Shanghai Jiaotong University, Tian Dong from Shanghai Jiaotong University, and Minghui Xue from CSIO. I would like to start this presentation by introducing the background of machine learning. And before I introduce machine learning, I want to introduce what is machine learning. So machine learning, basically, we have training data, and we have a learning algorithm. Together with training data and the learning algorithm, we can train a machine learning model. And once the model is trained, it can be used to predict testing data. So the whole process is called machine learning. So what is machine learning? Machine learning is quite similar to machine learning, but they have differences. The same, we have training data, but for some reasons, some samples in the training data need to be deleted. And this can be because of lots of reasons. For example, the right to be forgotten. Users has right to request their data to be deleted because the data can contain sensitive information of users. So when we have decided which data need to be deleted, and together with the trained model, we put them into an unlearning algorithm, and then we can obtain an unlearned model through the unlearning algorithm. Once the unlearning process is finished, then the unlearned model can be used to predict testing data, just like machine learning. So the whole process is called machine learning. But is there any privacy issue in the machine learning process? So we ask the question, what can be wrong in machine learning? We have know the process of machine learning, and we know machine learning will produce two versions of the model. So what will happen if an attacker can have access to both the model? And the motivation here is, with two versions of a model available to an adversary, machine learning opens a new attack surface for privacy linkage. In traditional attack surface, we only have the original model, and the attacker can only have access to the original model to infer the privacy of the training data. But in machine learning, because machine learning produces two versions of models, the first is the original model and the second is the unlearned model. Given access to both the models, machine learning has a new attack surface. Now we are going to introduce the research gap. So given the original model and the unlearned model to the attacker, existing work shows the membership privacy is further linked. And what is membership privacy? Membership privacy is usually linked by membership influence attacks. And membership influence attacks aims to infer whether a sample belongs to the training dataset or the testing dataset. But we observe that membership influence attack focuses on inferring the membership status, which is a yes or no question. So we identify the research gap. Can the confidential information within the unlearned data be inferred? Which means, can the confidential information of the unlearned data itself to be linked? So we propose unlearning inversion attacks to answer the research question. Unlearning inversion attacks aim to answer what information of the unlearned data is linked. And we identify that if the attacker can have white box access to the original model and the unlearned model, then the feature information of the unlearned data is linked. And this is we call feature inversion. If the attacker can only have black box access to the original model and the unlearned model, which is more strict than the white box setting, then basically the attacker can infer the label of the unlearned data. And we call the process label inversion. So in feature inversion, given white box access to the original model and the unlearned model, the research challenge here is, how can the attacker invert the feature of the unlearned data? The step one, calculate model differences. because the adversary has white box access to both the original model and the unlearned model. So the attacker can use the original model to minus the unlearned model. And the attacker can get a delta result, which is the difference between the two models. And the high-level intuition is the difference between two model parameters is the gradient information of the unlearned data, because the original model and the unlearned model only differ in the unlearned data. And the dimension of the gradient is exactly the dimension of model itself. So step 2, the attacker just leverages the gradient to invert the feature. And actually, this is well studied in federated feature linkage. So basically, the attacker can use optimization algorithms to recover the data to the feature of the unlearned data. And at the beginning, the inverted feature can be just like noises, but through the optimization algorithm and iteratively optimization, gradually the feature of the unlearned data can be obtained. So we show the basic results in our paper here. Now, let me introduce the results of feature inversion. We first investigate single unlearning case. In single unlearning case, the original model and the unlearned model differ in one sample. Now we have original unlearned data, and we perform feature inversion on both exact unlearning and approximate unlearning. Exact unlearning retrains the model from scratch. That is, retrain the model on the training dataset with the unlearned data removed. And approximate unlearning means it directly modifies the parameter of the original model to obtain the unlearned model that approximates the model retrained from scratch. And basically, as we can see, the feature inversion results on approximate unlearning is quite good, but on exact unlearning, the features are not visible. So the first takeaway here is approximate unlearning leaks a lot of feature information, while exact unlearning is safer due to randomness in retraining. We also perform multiple unlearning cases. In multiple unlearning case, the original model and the unlearned model differ in multiple samples. The same, we have original unlearned data. And we performed feature inversion in multiple unlearning case on approximate unlearning because approximate unlearning is much easier to be attacked. And the takeaways here is, as we can see, it is very difficult in multiple unlearning case for feature inversion. And even on approximate unlearning, not all the features can be inverted. But we notice that some features can still be inverted. And this means in multiple unlearning case, machine unlearning is also not safe from unlearning inversion attacks because some feature can still be inverted. Now we come to label inversion. So given black box access to the original model and the unlearned model. So the challenge here is how can we leverage the black box access to the original model and the unlearned model to invert the label? There are 3 steps. The first step is construct probing samples on the original model. Based on the black box access to the original model, we can construct some probing samples. And the probing samples is constructed so that the prediction confidence of these samples are equally distributed on the classes. For example, if there are 3 classes, then the prediction confidence of each of the sample is 1/3. So now we have probing samples. In the second step, we use the probing samples to probe the unlearned model because the adversary can have the black box access to both models. So using the probing samples to probe the unlearned model, we can collect the prediction confidence of these samples. So step 3, identify label by locating which class drops the most confidence. And we identify the label by locating which class drops the most. So if class A has the largest confidence drop, then we consider the unlearned data belongs to class A because it has the largest drop. And the intuition here is The class drops the most confidence because the corresponding samples of the class have been removed. Now we show some results of the label inversion attack. In single class unlearning case, which means original model and unlearned model differ in samples of one class, for example, class 0. And as we can see, class 0 has the largest confidence drop, so we can successfully identify the label of the unlearned data. And the takeaways here is both exact unlearning and approximate unlearning link label information. The second case is the multiple classes unlearning case, which means the original model and the unlearned model differ in samples of multiple classes. For example, class 0, 1, 2, 3, 4. And as we can see, class 0, 1, 2, 3, the confidence drop is among the top 5. So which means these classes can be successfully identified. And although we can identify all the classes, among 5 classes, we successfully identify 4 classes. So the takeaways here is both exact and approximate unlearning link label information in multiple classes unlearning case. So now we come to the conclusion and the future work of this paper. We discussed some possible defenses to defend against unlearning inversion attacks. The first defense is parameter of obfuscation, that is adding noise to the unlearned model. The second one is model pruning, that is prune the unlearned model. The third one is fine-tuning, that is fine-tune the unlearned model on additional dataset. All the 3 defenses is based on the intuition that we can post-processing the unlearned model to make the difference between the unlearned model and the original model inaccurate. So the unlearning inversion results is inaccurate. But the takeaways here is we found that the 3 possible defenses, they all lead to unacceptable privacy and utility trade-offs. So which means in the future work, we can propose some more advanced defenses to mitigate the unlearning inversion attacks. And the limitation of the unlearning inversion attack proposed in this paper is we found that it is difficult in multiple unlearning cases for feature inversion. And one possible reason could be because in multiple unlearning cases, the optimization process can be more challenging because we have multiple optimization targets. And future work of this paper could be focused on investigating unlearning inversion attacks on other domains. For example, like unlearning inversion attacks in other models or other data types, for example, like NLP domain. That's all of the presentation of this paper. Thank you for your attention. And for questions, you can reach me through this email. Thanks.